Hey guys, what's up? So we're here today with a two-dimensional collision problem, specifically a collision problem that has to do with a elastic collision. So without further ado, let's get started with the problem. So in this problem, we have two masses or two balls. We have ball A and ball B. Ball A has a mass of 0.20 kilograms and it has a velocity of 2 meters per second. Ball B has a mass of 0.3 kilograms and a velocity of 0 meters per second, meaning that it was at rest. Now, when ball A and ball B collide, ball A goes off at an angle of 53 degrees above the x-axis. And it goes above 53 degrees above the x-axis with a speed or with a velocity of 1 meter per second. And then we have ball B going in this direction. We're not sure at what angle and we're not sure at what velocity. And that's exactly what we need to find. And, the reason that we know that ball B is going in this direction is if you conceptually think about it, for ball A to be going in this direction, it must have hit ball B somewhere here. And if ball A hits ball B in this area, ball B must be going downwards at some angle. So you just have to use a little bit of logic and a little bit of conceptual thinking to understand exactly where these two balls go after the collision. So without explaining any much more, we'll go on to how to solve this problem. All right, so how I like to solve this problem is I always like to take the momentums of the balls initially, that means before the collision, and the momentums of the ball after the collision. But specifically because this is a two-dimensional collision, we have to take the momentums of the balls in their x components and their y components, both before the collision and after the collision. So let me show you. We have here in the x component initially. So we want to know the momentum of both balls initially in the horizontal component. So we know, let's first find the momentum of ball A initially. Now we know that the momentum of ball A has to be the mass of ball A times the velocity of ball A in the x component. So the mass of ball A we see is 0.20 kilograms. And the velocity of ball A in the x component is 2.0 meters per second because the ball is moving due east. So we know that it's going to be 0.2 times 2. And that is going to be 0.4 kilograms meters per second. Let's do the same thing with ball B. We have to find the horizontal momentum of ball B. And that's going to be the mass of ball B times the velocity of ball B in the horizontal direction. We see that the mass of ball B is 0.3 kilograms. And we see that the velocity in the horizontal component is 0 meters per second. So we know that the momentum of ball B in the horizontal component is going to be 0 kilograms meters per second. Let's do the same thing in the y component. So the initial, that means before the collision, let's look at the momentum in the y component. So we have to look at the momentum of ball A initially. That's going to be the mass of ball A times the velocity of ball A, but this time in the y component. That means in the vertical component. We know that the mass of ball A is 0.2, and we know that the velocity that ball A is going in the vertical component is 0. So it's going to be 0 kilograms meters per second. All right, and this is because there is no vertical velocities that are occurring in ball A. So we know that the momentum in the vertical direction is going to be 0 as well. Let's look at the momentum of ball E initially, before the collision, in the y direction. So that's going to be the mass of ball B. Let me fix that. The mass of ball B and the velocity of ball B in the y component. Once again, we see that ball B has no vertical movement, meaning that its momentum can't be in the vertical direction. That means that there is no momentum in the vertical direction for ball B. So let's compare this with the final momentums, both in the x and y components of ball A and ball B. Now, before I do that, let me explain why I'm doing that. I'm doing this because we have to understand that momentum is conserved in all types of collisions. What this means is, let's say that here we have in the x component a total momentum of 0.4 kilogram meters per second. That means after the collision, in the x component, the total momentum has to be 0.4 kilograms meters per second because momentum is conserved. This means that momentum is conserved both in the x component and in the y component.